Thank you, everyone, for attending our presentation on Magnol.Ai Plan and Execute. Today, we introduced an agentic AI framework designed to enable no-code analysis in digital health. Our goal is to empower analysis and healthcare professionals to perform complex data analysis safely, efficiently, and without the need for programming expertise. We appreciate your time and interest, and we look forward to your questions and feedback. Here is the outline of today's presentation. We'll start with an introduction to Magnol.Ai Plan and Execute and the challenges in digital health data analysis. Next, we'll walk through the platform's architecture and the key features, followed by a look at our agentic workflow and governance mechanisms. We'll then discuss future directions and conclude with the demonstrations and open Q&A. Magnol.Ai is a digital health data platform designed to host, manage, and analyze diverse datasets from connected clinical trials. This includes raw sensor signals, digital biomarkers, and participant-reported outcomes. What sets Magnol.Ai apart is its Plan and Execute framework, which leverages large language models to enable agentic, no-code data analysis. This means researchers can interact with complex data sets using natural language conversations, making advanced analytics accessible without programming expertise. Let's talk about the challenges of no-code analysis, especially in the context of digital health. As the clinical research data grows in volume, diversity, and complexity, traditional analysis tools often require programming expertise and manual workflows, which can be a barrier for many researchers. While no-code platforms promise easier access, they face several critical limitations in digital health, including limited flexibility. Many no-code tools rely on hard-coded workflows that can't handle the complex domain-specific analysis required in healthcare. Second, weak reasoning. These platforms often struggle with ambiguous natural language requests and inconsistent decomposition of complex queries, making advanced analysis difficult. Thirdly, inadequate governance. Without strong governance, there is a risk of irreproducible results, hallucinated code, and poor auditability, serious concerns in regulated environments. This slide we highlight the limitations of current approaches to no-code and agentic data analysis in digital health. Traditional no-code or low-code platforms are highly accessible and great for rapid prototyping, but they lack the flexibility needed for complex domain-specific analytics. They also struggle with ambiguity and can't easily encode healthcare-specific rules. LLM agentic frameworks like LangChain or AutoGPT are better at decomposing tasks and supporting flexible workflows. However, they come with significant risks. There are no guarantees of safety or correctness. Reproducibility is poor, and there is a real risk of plan drifting or the system hallucinating results, especially problematic in regulated environments. Finally, while healthcare machine learning practices offer strong transparency and mature validation. They are often not embedded into user workflows. Validation is manual and slow, and it's hard to scale these practices to multimodal sensor data or automate quality checks. These gaps underscore the need for a new approach, one that combines accessibility of no-code tools, the flexibility of agentic frameworks, and the governance and transparency required for digital health. The Magnol.Ai Plan Execute framework is an LLM-driven system designed for agentic no-code data analysis. Its core innovation is the ability to transform natural language goals into structured, executable plans, which are then carried out through governed tool invocation. The framework features a supervisor component that enforces governance, ensures compliance, and repairs plans as needed, resulting in deterministic and reproducible reasoning. What makes this framework unique is its dynamic assembly of workflows from a library of validated skills, allowing for complex domain-specific analytics without the need for custom pipelines. Governance is embedded throughout the process, with mechanisms for safety, compliance, and reproducibility. This approach bridges the gap between user intent and governed execution, making advanced analytics accessible, safe, and reliable for digital health applications. This slide contrasts the traditional passive approach to data analysis with the plan and execute. In the passive model, users are responsible for manually breaking down their analytical questions into smaller subqueries, writing glue code to connect results, and performing ad hoc checks with limited governance. This process is often slow, error-prone, and difficult to audit. With a plan and execute workflow, the user simply states their goal in natural language. The system's large language model generates an explicit step-by-step plan, which is then executed through typed tool calls. A supervisor component enforces governance, repairs plan as needed, and ensures that every step is validated and reproducible. The result is a fully traceable, auditable workflow that accelerates insights generation and reduces the risk of errors, making advanced analytics accessible and safe for digital health. This slide details the design of the plan and execute workflow. The process starts with the user stating their goal in natural language. The system then follows a strict priority order to achieve the goal safely and efficiently. The sensor is used by the system to explore the environment using Python code execution, retrieve grounded results directly from databases or data tables. Next, knowledge is used to assess contextual information, such as study metadata, table schemas, and domain knowledge. Internal sources are prioritized, but external sources like bin search can be used as a fallback. Finally, the clarification. If information is missing or ambiguous, the system proactively queries the user for clarification rather than making assumptions. This tiered approach ensures that the workflow is both robust and reliable, preventing speculation and maintaining compliance. By embedding these steps into the workflow, Magnol.Ai ensures that every analysis is grounded, auditable, and reproducible. This is a key requirement for digital health applications. This slide provides an overview of the plan and execute system architecture. At the core is a plan and execute engine, which orchestrates the entire workflow. The architecture is organized into several key layers: skill layer and the node layer. These layers represent the solution and the code views, respectively, allowing the system to dynamically assemble workflows from a library of validated skills and execute them as code. The supervisor. This component enforces governance, validates each step, and manages error handling and replanning to ensure safe and compliant execution. The sensor and knowledge modules. The sensor module handles code execution and data retrieval, while the knowledge module provides access to contextual information, such as study metadata and domain knowledge. The service and graph layers. These manage dependencies, data flows, and integration with cloud services like AWS and Azure. Finally, the governance and provenance. The system embeds governance mechanism throughout, capturing a detailed provenance log for every analysis, supporting auditability and reproducibility. This module and governed architecture enables Magnol.ai to deliver safe, flexible, and scalable no-code analytics for digital health and beyond. This slide explains how the supervisor component is implemented within the plan and execute framework. The supervisor plays a critical role in ensuring safe, compliant, and reproducible analytics. It decomposes user queries into a sequence of subtasks and enforces a strict non-assumption rules, meaning the system never guesses or speculates when information is missing. At each step, the supervisor validates progress through schema and rule verification, success flags from tools, and, when necessary, explicit user acknowledgement. If an error occurs, the supervisor can replan with adjusted parameters, retry the step, or request targeted clarification from the user. This approach ensures that every execution is grounded, auditable, and reproducible, which is essential for digital health and other regulated environments. This slide focuses on sensor components of the plan and execute framework. The sensor acts as a code execution engine, operating within a secure, sandboxed environment. It's responsible for running Python code and custom skills to retrieve and process data, generates outputs like numbers, texts, data frames, and visualizations, and provide detailed error tracebacks when issues arise. This slide covers the knowledge components of the plan and execute framework. The knowledge module is responsible for providing the system with the contextual information it needs to make accurate and compliant decisions. It uses a tiered approach. Internal knowledge, which is the priority. The system first assesses internal resources, such as study metadata, table schemas, and domain-specific protocols. This ensures that analyses are grounded in validated, organization-specific information. External knowledge, which is the fallback. If the required information isn't available internally, the system can leverage external sources, such as Azure Foundry Bin Search, to supplement its understanding. the knowledge also uses React paradigm. The knowledge module follows a reason before acting approach, meaning it carefully considers the context and available information before invoking any tools or making decisions. By prioritizing internal knowledges and only using external sources when necessary, the framework maintains both accuracy and compliance. This design supports robust, context-aware analytics and helps prevent errors or misinterpretations that could arise from relying solely on external data. This slide highlights the governance mechanisms that are deeply integrated into Plan and Execute framework. Governance is essential for ensuring that all analyses are safe, compliant, and reproducible, especially in regulated environments like digital health. There are several key mechanisms at play. Study and table affirmation. Before any analysis, the system verifies that the referenced study and the data tables actually exist and are correct. This prevents accidental cross-study contamination and ensures that the analysis is grounded in the right data. Manifest-based source selection. All data sources are checked against a manifest, which defines schema, location, and allowed fields. This blocks access to undeclared resources and prevents data leaks or unauthorized joins. Anti-pattern enforcement. This system detects and prevents risky behaviors such as unbounded table scans, unit mismatches, or missing data, ensuring only validated computations are allowed. Finally, provenance digest. Every analysis captures a detailed log of user intent, plan steps, tool calls, and supervisor decisions. This creates a deterministic replay log, supporting audits and regulatory reportings. This slide highlights how Magnol.AI enables no-code analysis for digital health and beyond. The platform automates both standard and ad hoc data engineering and analysis tasks, allowing users to interact with data using natural language instead of code. This approach covers a wide range of tasks, including data querying, visualization, analysis, processing, quality checks, anomaly detections, and insight discovery. This video clip demonstrates how Magnol.AI Plan and Execute framework enables no-code analysis of CGM data loaded from a CSV file. The user simply types a natural language request, such as show the AGP for the past 2 weeks. The system automatically interprets what AGP means and generates a step-by-step plan to retrieve the necessary data, process it, and produce the AGP plot, as you see here. This slide illustrates how the supervisor intelligently interprets the user's request, such as show the AGP for the past 2 weeks, and break down the tasks of generating an AGP plot into a series of well-defined steps. The workflow is fully agentic and governed. The system analyzes the user's goal, identifies the necessary tools, validates each step for accuracy and compliance, and ensures that the final results are both reproducible and trustworthy. This is a case study number 2, EDA data analysis. This video clip demonstrates how the Plan and Execute framework extends its capabilities to support vision-based AI insights. In this example, the system analyzes EDA, or electrothermal activity data plots, comparing results from before and after the occurrence of migraine pain. By leveraging multimodal AI, Magnol.AI can automatically interpret and compare visual data, uncovering patterns and differences that may not be immediately apparent through manual inspection. This approach enables more comprehensive and actionable insights, helping researchers and clinicians better understand the impact of migraine events on physiological signals. This slide summarizes how Magnol.AI vision-based AI insights are implemented. The platform leverages Azure OpenAI's Vision API to analyze images and plots generated by the no-code analysis tool. This enables the system to deliver piggyback insights, uncovering patterns and findings that may not be immediately evident through visual inspection alone. Magnol.AI can integrate images from multiple sources, including user uploads, session data, and external URLs such as Grafana dashboards. When a user requests image analysis, the system automatically determines the image source, processes it, and prepares it for multimodal LLM analysis. The AI then interprets both visual and textual data, answering user questions, extracting insights, and generating comparative reports. To summarize, Magnol.AI Plan Execute empowers users to explore and analyze complex clinical and sensor datasets through intuitive no-code interactions. By automating data labeling and embedding governance throughout the workflow, the platform delivers real-time, intelligent insights while ensuring safety, compliance, and reproducibility. In our discussion, we recognize several important considerations. LLM variability. Plans may occasionally require supervisor-guided repair, and reliability depends on prompt design and model tuning. Evaluation scope. Current results are based on small-scale, scenario-driven studies. Broader validation is needed for generalization. Runtime overhead. The framework may introduce overhead for very large-scale analytics. Dependency on curation. Effectiveness relies on high-quality manifests and registries. These points highlight both the strengths and areas for future improvement. We invite your questions and feedback as we continue to advance safe agentic AI for digital health. Looking ahead, our future work focuses on expanding the capabilities and the impact of Magnol.AI Plan Execute, including richer domain knowledge integration, expands sensor library, verifiable governance contracts, human-in-the-loop modes, broader ecosystem integration. These initiatives will help us deliver even safer, more flexible, and user-centric no-code analytics, supporting innovations and compliance in regulated environments. Thank you. Please submit your questions to Hui Zhang, Guangchen Yuan, and me in Eli Lilly and Company.